We've had sessions on side channel analysis, we've had session on post-quantum cryptography, and this is going to be the session on side channel analysis on post-quantum cryptography. Our first speaker of the day is Marcus Brinkman. And I think that's enough to be said. Marcus, take it away.
Yeah, good morning. I hope you heard me clearly. I think the microphone works. This work is joint work with me and Tichanuk doing Satyansub, Alexander May, Julian Nowakowski, and Yuval Yarom from Ruhr University Bochum, and Tichanuk is from University of Klagenfurt. So I will today show you how we can use a side channel to get the secret key in a McEllee system just from the key generation. I will not look at encapsulation and decapsulation. For that, there's a talk later, but by another group in the afternoon. So you can visit that as a basically follow-up talk for this work. Here I present you the classic McEllee's crypto system. It is based on problem encoding theory, and from its performance here wise, it's a competitive and decapsulation. It has very short ciphertext, but it has very slow key generation and large public keys. So it actually was a contender in the NIST competition, but it was not selected even in the third round because HQC won because of better performance characteristics for the applications. But it is not completely out of the use. There is an ISO standardization draft that also uses McEllee's in addition to MLChem and FrodoChem. And we can actually see use cases. If you have long use static keys, then you can use McEllee's. For example, Mulvat VPN deploys post-quantum cryptography with WireGuard and MLChem plus McEllee's, so it's a combination. And also the German BSI recommends classic McEllee's in addition to FrodoChem and MLChem. So it's still worth looking at. Classic McEllee's is defined by a couple of parameters. You need a field with 2 to the power of m elements, and then you have an ordered subset of that field, L. The size can be chosen to just for the public key size and security goal. And you also need a Gopper polynomial of degree t, which is something like 64 or 128. And the Gopper points, at least the order of them must be kept secret, and the Gopper polynomial also must be secret. Also, the Gopper polynomial doesn't vanish on any of the chosen points, which is important, as you will quickly see. When you when you have chosen all these parameters, then you can define this Gopper code. It's basically each column only depends on one of the chosen points, like alpha 1 in the first column, alpha 2 in the second column, and so on. And each column has a very rigid structure. It is the power of this point divided by the Gopper polynomial evaluation on that point. So you have, first you have the power of 0, so it's 1 divided by the Gopper polynomial of that point, and then you have all the powers. So each column, it's important to notice, only depends on one Gopper point and the Gopper polynomial. So that is, and only the evaluation of the Gopper polynomial on that point. So this is like 2 times m bits. And the whole column is t times m bits because each of these values is written as the vector, and then you put all the vectors under each other, and then you get t times m rows in this matrix and n columns. So this is the code. And how to do DN encapsulation, as I said, is not part of this talk. What is important here is that from the secret key matrix, we establish a public key just by Gaussian elimination. So we bring this code in its so-called systematic form, which just means that the square to the left is the identity matrix and the rectangle to the right is the public key. So this is a sort of compression because the public key gets smaller, and also this public key completely hides any structure of the Gopper code. It's a difficult problem to go back from this public key to the secret key matrix. We don't know how to do this efficiently, and this is where this gets its security from. Okay. So our attacker goal is to use this public key and a side channel in the Gaussian elimination to reconstruct the secret key. And if you have the secret key matrix, it's also clear that you can derive everything, because in the first row you get n points, n evaluations of the Gopper polynomial, and then you can use Lagrange interpolation to get the whole polynomial. And in the second row, you can just multiply by these evaluations of the Gopper polynomial, and then you get the alpha 1 to alpha n, okay? So once you have the secret key matrix, it's clear that you have the whole secret key. So Gaussian elimination, we have to dig deep into this because the side channel comes from there, but I hope I can show this without getting too technical. The intuition is clear. Gaussian elimination proceeds column by column. So to get the systematic form, we first look at the first column, and then we do these row additions that we all learned in school to get the first vector to be 1 and then 0, 0, 0, 0. And then we do, then we have one good vector where we can then proceed to the second column, because everything we do in the second column, for the second column, does not change the first column anymore. So by going column by column, after TM columns, we will have the systematic form. And we need to understand how each of these columns work. So in the beginning, so also I should mention, during this process, this whole matrix changes, right? The row additions do not only change the left side, they also change everything in the right side. This is why the public key is completely obfuscated. This is the reason why we cannot just like take the whole thing. We have to look at each column. And in the first step, we initialize this following matrix with the current one. And then we have two stages, diagonal stage and zero stage. In the diagonal stage, we first try to get the 1 on the diagonal, and in the zero stage, we try to get a 0 everywhere else. And this is very simple. If there already is a 1 in the diagonal, we don't need to do anything in the diagonal stage. If there isn't, then we need to find a 1 somewhere else and then add it to the row J, and then we get a 1, right? So that's simple. And for the zero stage, we do the opposite. We now have a 1 in row J. So we look at every 1 in every other row, and then we add row J to that row, and then we get a 0. So I don't know. I actually hope you remember this from school. So the result will be that the column J will be in the systematic form. Okay? And what's important to see here is there is an if condition here and an if condition here. And we can now hypothesize that there's some way to leak this conditional. And this would actually leak all the bits in that column at the step of Gaussian elimination. Okay, so what can we do if we leak all these bits? Well, each column, before it is eliminated, defines the actual row additions that are to be done based on the algorithm I just showed. So if you leak all these columns, then you actually leak all the row additions. So you can reconstruct those row additions, and then you can take the public key, put the identity matrix in front of it, and then you can apply all these row additions in reverse, and then you actually get the secret key back, right? So this would be very simple, but this is without noise in the side channel. So what I told you in the beginning is that I would show you how to do this with noise. So now we have to take a different strategy, because if we would take the same strategy and there's a bit flip somewhere in our side channel, then we cannot reconstruct the row additions, we get the wrong row additions, and then the reconstruction will be completely wrong, right? So we have to find some other strategy here. So what we use is actually we observe that every column only depends on two values in F. So we take all the possible columns of the first column. This is basically all possibilities for alpha and all possibilities for G of alpha. So that is only a 2 to the power of 2m, a little bit less because G of alpha cannot be 0. And then we have a codebook, and then we can use this codebook to correct errors in our side channel of the first column. Now, how many errors can we correct? This is actually insane, right? We have 2m bits. We have 2 to the power of 2m of the size of the codebook, but we have 2 to the power of mt possible columns. So, for example, in numbers, that would be 2 to the power of 26 for the largest security parameter set, decoding a vector in 2 to the power of 768. So this is a very sparse codebook in a huge space, so we can actually expect there to be a huge decoding radius, so we can correct many errors. By just searching for the nearest vector, based on the Hamming distance in this codebook, it's called maximum likelihood decoding, then you can try to find an error-corrected version of your leak. And then you actually know the real row additions that have been done by the algorithm, and then you can apply those row additions to the whole codebook. You can update the codebook, and then you get all the candidates for the second column. And also you can remove some entries because you can optimize it, because now with one alpha chosen, all the other alphas have to be different, so you can eliminate those from your codebook. But that doesn't actually matter too much. So now we have an updated and reduced codebook for the second column, and we then iterate over this process until we have enough information to do something more interesting. Because, I mean, you could run this algorithm all the way through, but there's something interesting that happens after decoding t+1 columns. Because now we have enough information. We have the first t+1 alphas, and we have the evaluation of the Gopper polynomial on t+1 distinct points. So we can now use Lagrange interpolation to get the whole Gopper polynomial. And once we have the Gopper polynomial, we can actually, we only need to know the set L and its order. And now we have a distinction in cases, because depending on how Beckley's is implemented, we either have the case that we do not know the set L, so we need to know also the points of alpha and their order, then we just can continue this algorithm with a much reduced codebook, because now the codebook only depends on alpha, not on the Gopper polynomial. I mean, each entry has a fixed evaluation of the Gopper polynomial, and then the codebook is only square root in size of the original codebook, and everything gets much easier. Or if you know the set of alphas, then you can be even smarter, because now you only need the order, and we have a better algorithm for that. It's complicated, I can't get into it here, but it's called Sendry's support splitting algorithm, and everybody just says this and moves on. But if you actually want to take a closer look at it, because we did, we actually implemented this algorithm and evaluated that it heuristically works in our setting. So yeah, so these two cases are. The second case is actually useful, because the maximum parameter set in classic Michaelis just uses as the set L the whole field. So we actually do know the number of the actual points and just need the order. Or also in implementations like Botan, also the number of the set of Gopper points is known except for the order, and then we can use this strategy. Okay, so how well does this work? We have a precise analysis in our paper, but here I will just give you the intuition and show you that the intuition is actually already very good. I said each column has as information tm bits, and the required information for key recovery for each column is only 2m bits. So the relative information required is 2 divided by t, right? The m cancels out. So we actually have a formula for that. It's called the binary entropy function, and that tells us the information loss for an error rate tau. And here we take the inverse and then take 1 minus that to get the accepted the number of the relative information preserved by an error rate tau. So if we take this equation and set it to 2 divided by t, then we actually get an acceptable error rate of 42%. So 42% of the bits can be completely wrong. Just flip randomly, and we still can recover the secret key, which is pretty good. So, for example, if the error rate would be 1/2, then we wouldn't know anything about the secret key, because that would be basically just a random bit flip, right? If we compare this with other attacks in the literature, classical algorithms as well as post-quantum algorithms, then we see that we are far above every other acceptable error rate. For example, we have error rates for rainbow under 30%. We have also very small error rates for some strong cryptographic schemes like Kyber and New Hope. And so this is actually this huge redundancy in the Gopher code is an actual problem here when considering such channel leaks. Also, interesting to see that the error rate that is acceptable increases when the parameters get higher. So if you take a higher security parameter like t increases, then the acceptable error rate will be larger and larger. Our hypothesis is that this actually approaches 1/2. Okay, so practical evaluation. We don't just want to do theory, we want to do actual hardware measurements. So we looked at 2 algorithms, and I will only cover classic Michaelis here. This is the source code from classic Michaelis implementing the Gaussian elimination. And I won't go into detail here, but it's important to see that there's no if here for the Gaussian elimination, because it's using constant time coding techniques, right? So the set of row additions is always the same. All rows always get added to everything else, but they are masked. So sometimes the row addition is actually performed, and sometimes it's just a no operation. And we can see this here in the mask parameter, which actually depends on this entry in the execution matrix that corresponds to the if condition that I showed you before. So here we don't want to leak an if, but we do want to leak the mask. We were pretty sure that there's some way to find this leakage. So we did a test vector leakage assessment by taking 1,000 random keys and 1,000 fixed keys, and then we take the average and subtract it, and then we get the interesting point of the point that maybe leak, right? So we did a differential power analysis. Here on this hardware, we took an ARM STM32L592, and then we ran the Gaussian elimination for Michaelis on this device, and we used the chip whisperer to measure the power consumption. And here we even looked into the assembler code and found the place that is a potential leakage. It's a signed bit field extension that expands this mask value from a 0 to a 30-bit 0 and from a 1 to a 30-bit -1. So that is actually something that is known to leak. There's a paper which identifies this instruction to be leaking in power. And here are the traces. So this is the full line here is the average case for random keys. And then we separate those with a mask 0 from those with a mask 1. And the t-value, the statistical significance of the separation is here in the yellow line. And you can see that the t-value here is like 17 or something. It's a very large number, so we get very good separation on a single bit leak here. So, but the single bit leak is not enough, right? So with Gaussian elimination, we actually have very long traces. So this public key generation is slow, as I said in the beginning. And each trace was like 69 seconds of measurements running, I think, at 10 megahertz. So we get very huge traces 28 million samples corresponding to the same number of CPU cycles. This is 400 megabyte per trace. And then the implementation, because it's constant time, it also has a lot of points of interest. So we are looking for 420,000 points of interest in this trace. So aligning the traces was simple because of constant time coding techniques. And I'm glad to say that the actual, after some tuning of the time modes, etc., we actually got very stable measurements, and I could capture 3,000 traces in 2.5 days, producing 1.2 terabyte of data. And then we processed this data and applied the t-statistics and found the points of interest that I showed you before. Here now is a zoomed in version of the t-statistics for the trace. Like if there's a larger blue here, then there's a more statistical significant separation of the traces. And you can see that there's a very strong signal here, and each point here corresponds to one loop iteration of this, basically it corresponds to one of the row additions. So this is just an excerpt because we have 420,000 of those. And to actually determine where these points of interest are and how they correspond to the code, we use Fourier analysis to find the cycle lengths of the loops. And then we also identified this skip for if I is equal to j, then there's a little bit skip, so the loop is not completely homogeneous. And then we arrived at a precise model for the points of interest. So even if some points of interest are missing from the data, we can still reconstruct them because of constant time coding. They are at precisely the point where we expect them to be. So we implemented all of this, and then we ran 10 tests, and in all the 10 cases, we could recover the secret key using the Sindri support splitting algorithm. And to show that these results generalize, we also ran some experiments, not on real hardware, but on simulated traces, simulated leaks. And we see that our actual analysis that I didn't show you here corresponds very well to the experimental data. So the lines are our prediction for how the algorithm behaves, and the dots are the actual simulation from our algorithm applied to simulated leaks. And what we see here is the error rate that is acceptable. And if you take, for example, a success probability of 1/2, then you can here see that the error rate for higher security parameters, it approaches this value of 0.42. It doesn't reach it completely, it stops at 0.4, but if you increase t, then you can get even further. So yeah, so just a quick word on countermeasures, and then I will conclude. I don't know how to prevent this, so you have to tell me, because I only know about attacks, I don't know about countermeasures. But I heard about some ideas. So, for example, we can increase m. This makes the codebook larger and makes the attack harder. But increasing m is stupid because then you also need to increase n and t, and everything gets much slower. And classic Michaelis is already struggling, right? So this is not good. Then you can try to mask the Gaussian elimination by applying an invertible matrix S to the Gopher code, and then, of course, the codebook doesn't correspond anymore to the actual columns, and the leak doesn't work. But you need to hide this S and also the matrix multiplication. You have to tell me if it's worth it, if masking of multiplication of two matrices and generation of an invertible matrix is easier than masking the actual Gaussian elimination. I don't know. Also, it doubles the cost for key generation. And then you can apply hardware masking, but we heard yesterday in the keynote that this will actually, this is possible. You can mask a Gaussian elimination, but it makes everything much slower. I think it was a factor for first order masking, a factor 15, and for third order masking, 67. So this is all also very expensive in terms of actual hardware. I don't know. People have to figure this out. So the summary of my findings, we showed you how to reconstruct classic Michaelis secret keys from a leaking Gaussian elimination. We have very good error recovery, approaching 40% of bit flips. And higher security parameters allow for larger errors, and hardware implementations need to figure out how to protect against this. Thank you for your time.
Thank you, Marcus. I think we have time for 1 or 2 questions. Are there any questions in the audience?
First of all, thank you very much for your talk. I have 2 questions in one. First one, the assumption that you have an access to some information about all T times M Gaussian eliminations, how mild do you find it? And what happens if you miss an information about a single Gaussian elimination, like completely, let's say it's broken beyond restoration?
What do you mean by single Gaussian elimination? One column or one trace?
Yeah, you missed
Okay,
one trace
yes.
completely.
So thank you for your question, because I forgot to say that every attack we did was a single trace attack. So you just take one measurement and then we get the secret key. So that's important, thank you. And the other question, yeah, I mean, this is a large leak, 69 seconds of actual measurements, but each bit is independent of everything else. So I assume if you can measure one bit, then you can also measure the other bits. Like, I don't know about scenarios where you can only measure for 10 seconds and then you get kicked out of the room. That would be something interesting, but I think like it's a long leak, but every part of the leak is equally difficult. So maybe that answers the question. Because of constant time, it's perfectly aligned anyway.
Okay,
yeah, I hope this answers your question.
All right, I propose we go to the next talk. Let's thank the speaker again. And then I will ask our second speaker. Our second speaker is Wei Wang. Let's welcome him with an applause. Okay, you have the floor.
So, waiting for the slides. This is not. It's not the first slide. Go back to the. It is still not the first. Okay, thank you. Sorry for the late. And I'm Wei Wang. I come from Shandong University, so it's a great honor to be here to present our paper entitled "Reject Sampling, Reject Signatures Challenge Pose New Challenges: Key Recovery of Dilithium via Side Channel Attacks." This is a joint work with Zhou Yuanyuan from Synopsys, Sun Yiteng from Shandong University, and Yu Yu from Shanghai Jiaotong University. First, I will give a quite short background. So side channel, first background should be side channel attacks. A cryptographic primitive is implemented and run in a given environment. So it means that it may have some side channel leakages, just as power, time, or even faults. So an adversary is able to exploit this side channel leakage to recover, for example, the secret key. In this work, what we want to do is we provide a new side channel attack method to the MLDSA, which is basically dilithium. And here I also provide it's a quite brief introduction for the sign procedure of dilithium. And we can see that the sixth line is quite important because many side channel attacks exploit the leakage of intermediate values of the line 6, that is Y or CS1, to recover the value of S1. Once the value of S1, which is part of secret key, is recovered, attackers is able to directly forge the signatures. So And another thing we want to notice about the sign procedure of MLDSA is that it uses the reject sampling to remove the dependency of Z and the secret key S1. So basically what it do is it just check the norm of Z to find if the norm is larger than some bound, then it will reject the cube of Z, which is response, and C, which is the challenge. This reject signatures will not be output from the sign procedure. But what we want to do is we exploit the leakage from the reject signatures to recover the secret key S1. Sorry. Here we also provide a quite short summary of existing side channel attacks on MLDSA. So it should be noticed that we provided the first practical side channel attack using the leakage from reject C and Z to recover the secret key. And our attack type should be the profile simple power analysis. Then I will provide the details about our attack method. In the left part, I will provide the procedure of signatures for reference. So first of all, I will present the range of some important intermediate values. First of all, our goal is to recover the private key S1. What we focus on is the line 6, which calculate the addition between vector y and CS1. The result should be z. And we know that the range of the coefficient in y should be minus gamma 1 to gamma 1, and the range of c coefficient should be minus 1 to 1, which has 4 non-zeros because it is polynomial, and the range of CS1 coefficient should be minus eta to eta. So we can, since C is polynomial, S1 is also a vector of polynomial, so basically CS1 is the multiplication between two polynomials. It means that we can calculate the range of the coefficient in CS1, which is simply minus 4 times eta to the 4 times eta. We can rewrite it as minus beta to beta. Okay, so let Zi be a coefficient of Z, and let Xi and Syi denote the corresponding coefficient of CS1 and S1 respectively. Then we have this equation, which is quite simple because we just rewrite C as the polynomial C as a matrix, and we can see that if we know the range of the coefficient of CSE, for example, if we know a range of Xi, then assume that we already know the value of C, which is challenge, and we can build inequalities for the value of CS1. So when a coefficient Z here is null, so when a coefficient Z here, if this is null, we can calculate the range of CS1, which is narrower than minus beta to beta. Okay, so if a coefficient Zi is null, say it equals Z, then the corresponding Xi, which is CS1, lies in the new interval, which is this to this. The upper bound should be maximum of minus beta and Z minus gamma 1. The upper bound should be the minimum value between beta and Z plus gamma 1. So we know that we can see that if we know the value of Z and Z is the absolute value of Z is quite large, then this interval will become narrow, and it means that a large absolute value of Z leads to a narrow range for the corresponding CS1 coefficient. Let me give a example. So if we know when zi is null, say it equals z, it means that if the reject zi equals, it is rejected and it equals minus gamma 1, then we can see that the coefficient of CS1, which is x1, is minus beta to minus 1, which is narrower than before. The other two cases are similar. So it means that we can collect multiple tubes of reject C, Xi, Zi, which yielding two inequalities for constructing an ILP instance. Okay, but we have a bad news that we cannot directly recover the reject C because normally in a side channel attack we cannot assume that we can directly recover any random variables using a side channel attack. If we can do this, we can directly recover the value of secret key. But we have a good news that we can usually recover recover the Hamming weight of a secret value or of a value. But multiple values corresponding to one Hamming weight. For example, we know that the Hamming weight of 1 is 1. We also know that the Hamming weight of 2 is also 1. And the Hamming weight of 4 is 1. So when we know that the Hamming weight of a value is 1, we don't know actually what value it is. That is the problem. But there is also a good news that there exists some Hamming weights uniquely determine certain z coefficient. Those values can be recovered by first determining their Hamming weights. So I will give an example using statistical analysis. Let's consider we target on MLDSD 44, the L2 security level. Here we found that if the rejected D lies in the range of minus gamma 1 plus 1 minus beta to minus gamma 1 plus 1 plus beta, it means that it is negative and it is rejected. In this case, we found that the Hamming weight of 15, 31, 21, and 25 are unique. And among them, the Hamming weight of 15, 31 corresponding to minus gamma and minus gamma 1 minus 1 are of particular interest due to their relatively higher frequency. So it means that these two Hamming weights are unique. And similarly, we also check for other range of the z coefficient. If it lies in the range of this one, it means that it is rejected and it is positive. And we found that these four Hamming weights are unique. And among these, the Hamming weight of 16, 1, corresponding to gamma 1 minus 1 and gamma 1 are particularly interested due to their relatively higher frequency. Okay, so then we have a full specific choosing Hamming weight, and we provide a simulated attack, and we assume that any rejected zi which full specifically chosen Hamming weight along which the corresponding c can be recovered with 100 accurate. The number of leakage signatures required should be less than the 3 million, and the running time of ILP is less than 4 minutes. So next I will show how to recover the value of C. Because C here it is rejected, it will not output it, and the value of Hamming weight of Zi. And we use a case from real side channel leakage. So first I will provide the attack setup. The target should be the reference implementation, and we run it on 32-bit STM32F microcontroller running at 8 amp hertz. And the power trace equipment is picoscope 5244D oscilloscope, and we set the sampling rate to 62.5 hertz. We use multilinear perception neutral network model as the template building method. Here we also provide some parameters for this model. To recover the C, our attack point should be its entity procedure. Its entity procedure. So what we do is that first I will provide in the left part I will provide a entity which eight coefficient, and then we divide the coefficient here as two types, the up type and the lower type. What's the difference is that for the up type, the blue one, this coefficient will be multiplied by the Twitter factor, say zeta. Yeah, this is upper coefficient, and others are lower coefficient. They will not be multiplied by the Twitter factor zeta. And this is also upper coefficient. This is also upper coefficient. This one, this one, this one. So yes, yeah. Okay. It means that I will repeat that the upper coefficient are those that will be multiplied by zeta. Okay. So let's consider C2, C5, C6, and C7, which are input upper coefficient. This coefficient can be recovered directly. Why? Because the Hamming weights of Ci and Ci times zeta are quite significant with different value of Ci. For example, when Ci, a coefficient Ci equals -1, the Hamming weights of Ci and Ci times zeta are 32 and 14. When Ci equals 0, the Hamming weight should be 0 and 0. With Ci equals 1, the Hamming weight is 1 and 90. So the difference is quite significant. We can directly recover the value of these four coefficients, C4, C5, C6, and C7. Let's consider a lower coefficient, C3. Because this coefficient will not be multiplied by any Twitter factor, we cannot directly recover the value of it. What we do is that first we found that this one and this one, C32 and C72 are determined by C3 and C3 and C7. And if we know C7 and if we know C7 and C32 and C72, and we can directly recover C3. But the bad news that we also cannot directly recover the value of C72 and C32 because the range of this upper coefficient is not restricted to -1, 0, and 1, unlike the input coefficient. What we can do is that we can recover the noise Hamming weight of them. So let's denote H32 as the Hamming weight of C32 plus some tolerance. And S72 denoted as, we denote H72 as the Hamming weight of C72 plus some tolerance. In this case, the tolerance will relate to the SNR of the side channel leakage. The higher SNR leads to smaller values of the tolerance. Okay, then we can give a DPA style method. First, we exhaustively guess the value of C3, this one, and calculate the hypothetical values of C32 and C72. Then we compare the hypothetical Hamming weight of these two coefficients, which H32 and H72. So the high similarity outputted from the computation hints the correct guess of value of C3. Similarity, we can also recover the value of C2. And then we go to then they move to the lower coefficient C1, this one. So for this one, we need to consider these four coefficients. Then we can assume that we can recover the noisy Hamming weight of these four coefficients. The DP style method is similar. We exhaustively guess the value of C1, this one, and then because we already know the other coefficient from C2 to C7, then we can exhaustively we can calculate the hypothetical value of these four coefficients. Then we compare the hypothetical Hamming weight of them with the observed noisy Hamming weights. The largest similarity output from the comparison hence the correct guess. The only left coefficient is C0. But it is quite simple because we can directly determine if C0 is 0 or non-zero, because we already know other input and we know that the number of non-zero coefficient is tall. So if we find the C0 is 0, then the recovery is complete. Otherwise, we can still directly distinguish between 1 and -1 because they are, thanks to their significant different Hamming weight. So we finished the recovery of C. Here I also provide some attack result. The orange curve shows the prediction accuracy for the Hamming weight of the internal coefficient. And we can see that with the increase of the tolerance, the prediction accuracy becomes 1. And then we also provide the success rate, which is the blue curve for the recurrence of the input lower coefficient. We can see that with the decrease of the tolerance, the success rate reaches 1. So it means that when the tolerance equals 3 in our setup, our attack both prediction accurate and success rate becomes 1. It means that our attack can recover the value of C, which 100% is successful. And we consider recovery of Z because we only need to consider 4 unique Hamming weight. The recovery of Z can be quite simple. What we do is that we collect several positions that manipulate the value of Z. First, attack target should be in the polycheck norm function of the reference code, which is here. It checks the bound of the value of each Z coefficient. Here. Another part should be the calculation of Z, which is addition between Y vector and CS1. And it's related to 2 functions, polyadd and reduce 32. Okay, so here we combine all the 3 attack positions, and we found we use the MLP to build our template and recover the value of recover the Hamming weight of C, because we consider 4 unique Hamming weight, and then we found that we can directly distinguish whether the value are the 4 unique values or others. We amount our attack which 5 million times, and all of the times are successfully correctly distinguish the Hamming weight and the values. Okay. Then we can recover the value of the Hamming weight of Z. Thank you. Any questions?
Okay, we have plenty of time for questions. Thank you for your good time to talk. Are there any questions for the from the audience? Okay, not yet, so I will start. Sorry if I missed this, but how many traces did you need for the training and for the attack itself?
For the training, we use 10. Maybe I think less 10,000.
Okay.
And for the attack, it is simple power analysis. We use attack for each trace. So.
Okay, and how well will the attack method hold up if you have more noisy traces? Like, how susceptible is it to noise?
I think this one is, and this finger. So what we do is we recover, when we recover the C, the value of coefficient of C, we consider the noise in the traces basically impact the prediction accurate. Here, the prediction accurate is the prediction of the Hamming weight of the internal coefficient. I think this one, the Hamming weight of them, because for this coefficient, it can be directly recovered because the only possible values are -1, 0, 1. But these values are not so narrow. So in this case, we need to recover the Hamming weight of them. But because of the noise inside of them, we cannot recover the Hamming weight directly, but we can recover the noise part of them. Yeah. So in this case, we add some tolerance here. So the large tolerance leads to the large tolerance leads to a larger value of the prediction accurate, but it will lead to a smaller accurate success rate of the input coefficient.
Okay, thank you. Any other questions? Yes, please.
Good question. Yeah, countermeasures. We believe that the only countermeasure should be masking, and maybe some shuffling method or some other hiding method help, but we don't know. It's I think the most security guaranteed countermeasure should be masking.
Okay, thank you. I think we can leave it at that. Let's thank the speaker again.
Thank you.
Our last speaker of this session is Jian Guo. Can we get his slides on the screen? All right. Can you go back? Great. Jian, go ahead.
Thank you. Good morning. I'm Chen, and we'll talk about multi-value plain text checking and full decryption Oracle-based attacks on HQC from offline template. This is joint work with Haiyue. So we know that HQC has been selected as this by NIST as a post-quantum standard in March 2025. It is based on well-studied problems in coding theory as a strong backup for this lattice-based standards Kyber. So at the current stage, it's really urgent to understand the implementation security of HQC before it is widely deployed in our digital infrastructure. So we go with the side of multi-value plain text checking and decryption-free Oracle-based attacks. These attacks are kind of hot topics in lattice-based crypto attacking Kyber, and has been highly effective and successful in lattice-based crypto, but it's still an unexplored open challenge in code-based crypto. It's mainly because, for instance, if you think HQC, it has a much more complicated decoding or decryption procedure, and also it has this much larger dimension, and it has very sparse secret key compared with lattice-based schemes. So we don't have a very good tool to extend the attack from this general plain text checking Oracle to this multi-value or more advanced multi-value PC Oracle and full decryption Oracle before. But now this CHES, we had this OTPCA framework, and based on that, we can actually solve this problem and achieve very high effective key recovery. So in this paper, we propose the very first MVPC and full decryption Oracle attacks on HQC. Let the results speak for itself. So you see that previously best So previously, the best numbers for 460 for OTPC. If you use MVPC, then we can reduce it by 40%. These FD oracle are extremely more powerful. You just only need 2 choices. So I organized the talk in the following ways. First, I will present some background information. Then I will detail the new attack methods, like the new MVPC oracle attack and the new FD attack. Then I will present the experimental validation. Finally, I will conclude the work. So let's briefly look at HQC. So the keygen looks like this. You have so you have this secret key of x and y. They are sparse polynomials. Then you generate a uniform H and compute S in this format, in this way. So this is public key. For encryption, we need to compute ciphertext UV, and we need to generate some intermediate sparse polynomials R1, R2, and E. Then we compute UV in this way. So the decoder will receive this value, and after some simple calculation, you can see that this is actually the encoding of M plus this small noise term A prime, because these are all small, all sparse polynomials, so the Hamming weight of this E prime is very small, and with overwhelming probability, the decryption success, so HQC actually provide the rigorous decryption failure rate analysis. In some rare case, the weight is too large, then you got the decryption failure, but the probability is very, very small. So, like other PQC CAM, HQC achieves indecisive security by CCA transform, like this Fujisaki Okamoto style transform. So this incaps and decaps looks like this. And another important property to mention is this decoding procedure of HQC. It actually employs this concatenated read Mueller and read Solomon codes. So the input to decoder is V. You can see that the length is N1 times N2. We first group them into N1 blocks. Then each block you have N2 bits. Then each block will feed to a read Mueller decoder and got output. So you will apply this read Mueller decoder for N1 times, and then you concatenate the output and feed it to the read Solomon decoder. So let's briefly introduce this oracle types. So this type of attack are based on plain text checking oracles. So roughly you can think, for HQC you can think it as the decryption failure oracles just tell you if the decryption success or decryption failure. This is a binary case. Then for MVPC, you have a more enhanced version that it can distinguish which message from a small predefined plain text set was decrypted. So you think that like binary is just a success and a failure, but multi-value you can decrypt to M0, M1, M2. You have like a set, and the oracle tells you which one it is. So you can get more bits of information from this MVPC oracle. So it has relevance in not limited to side channel attacks, but also in key mismatch attacks and fault injection attacks, because literature shows that from these attack surfaces, we can also build MVPC oracles. So the most powerful type in this class is full decryption oracle. So it has this high parallelism. In Kyber, you can think that the full decryption oracle, it just kind of outputs the full messages. But in HQC, we define it as an oracle that returns the parallel outputs of all N1 read Mueller decoder outputs in a single query. So if you think Kyber as decode or decryption as concatenated coding, like the outer code is identity code, then you can unify this viewpoint, these two viewpoints. So for the attack, we consider side channel assisted chosen ciphertext attack, which means that we assume that there's device running this decapsulation procedure for this HQC CAM, and this attacker or adversary craft the chosen ciphertext and send it to the device, and the adversary also measure the side channel leakages and try to create this oracle and do full key recovery. So let's briefly explain this OTPC framework. This is also published in this year's CHES. The core idea is like we can create pre-computed offline templates to estimate the likelihood of each secret key of being 1, given this PC oracle output. So it includes 4 phases. The first phase is kind of you try to optimize E, and then build a template, and then do this online attack and apply the template and got this reliability score, and then you do post-processing, use simple modified IST algorithm exploiting this soft information. So let's see this example, maybe a bit ahead, but it's roughly, you can select this intermediate value and generate this UV of this format. So you can think that, okay, we have a E, so this is a message, encoding a message. You can think that this part to be, you default choose them to be 0, then you can remove this part, but you just kind of place one arrow vector in this decoding vector space. Then you can see that we can actually add a small part of secret key as a perturbation. So let's go back. Oh, sorry. Let's go back. Yeah. So it's like in the attack case, it's like, okay, you stand there, and then there's more perturbation, depends on secret key. It can go to here, go to this message 1, go to message 2, message 3, but you don't know how, because this is secret part, you don't know. So the idea is like, okay, we can generate this, because we know the secret key distribution, we can generate this secret key by ourselves. We just generate a lot of secret key, and then we just say, okay, we kind of classify them. Okay, this kind of secret key goes here, this kind of secret key goes here. Then we can just group them and try to do statistical analysis to see like which bits are more likely to be 1 in this group of keys if it goes to M1 or success or anything. So this is just the idea of like building template. It's like, it's roughly just we kind of separate this key space, and if we see a decoding output, we know that it belongs to this kind of key space and should follow this kind of like statistical property that we call it offline templates. You know that this kind of template, we are not templating a device or templating a secret key, we are templating the decoding of HQC. So it means this optimization, we need to do some optimization. So this optimization, we just need to do it once, and it can be like this optimized vector E or this generated corresponding template. You can store it somewhere, and if someone wants to attack, then they can just use this result. So it's not part of the attack cost. So, sorry. Okay, let's move on to MVPC attack. So, so for MVPC attack, we partition the key space into several parts instead of 2 parts for this binary PC case. We select, yeah, we have talked about this, and we select R1, R2, and target this Y and X separately. You can see that we kind of add the E, and then this secret key as a small perturbation. And this, we configure E in this format. You can see that we just play a small, we just put a small pattern of length N2 here for HQC 128, it's like 384 bits. Then you have this N1 minus 1, the rest blocks, you either place it with all 0 blocks or you place it with all 1 blocks. Actually, we put this number of all 1 blocks, it will go to this decoding boundary and easily create decoding failures. So then we just try to optimize this epsilon using a simple genetic algorithm. we try to maximize this entropy of the calculated decoder's output, because this is just like the Oracle output. We want to maximize the entropy. Then when we observe the result, we get the maximum information. So there's a trick called this x to the power of k, because you see that only this part is sensitive to this secret key. So we can only, each time we can only trigger a block of length n2. So it means that we need to do this shift and try to shift this secret key blocks to the first block, and then we can cover all the parts of this secret key. So, oh, sorry, how to control that? Yeah. So this is this constructed offline template is also intuitive ways show the gain. You can see that the right part is the MVPC template. This is a part is offline template for binary PC Oracle. You can see that, okay, the red line just represents this a priori probability. If you have no decoding information, each bit are equal and with probability like W over N, which is a very small value to be 0. But you see that if you see this offline template, then some bits are very likely to be 0 and some bits are more likely to be 1. You got this soft information. But if you look at this MVPC, you see that we have, in this case, we have 6 messages, and we see that there are more Davids. The difference is higher, so you say this bit is more likely to be 0, and some bits are, these parts are more smaller. So you can that the difference is larger. The reasons our method divides the key space into more partitions, and each Oracle queries provide 1.9 bits of information compared to 1 bit of information in this binary case. So we get more information. So how to do online attack? You remember that we create, first we have this x to the power of k trick to shift each block to the first block, and we construct ciphertext as this format, and E is of this format. This epsilon is like this optimized pattern, and we query this MVPC Oracle to get two T decryption outcomes, so we need T patterns. Then we got this output. Then we just kind of querying this corresponding offline template and got the conditional probability for each bit. Then we just multiply them. Then this value is this reliability score we want to have. Then we just feed this this vector with this reliability score to this information set decoding algorithm. This is a modified algorithm adapted from this OTPCA. It's actually based on this nice CNGO ISD framework, but instead of typical ISD, you just sample this information set many times, but now we just do one pass decoding, and so we just put this matrix to this course standard form. Using this reliability score, it means that we put this positions are most likely to be 0 at the beginning. We can think that this these first positions are most likely to be 0, so we can assume that T1 positions are error-free. So this kind of reduces dimension of the matrix and makes it simpler. So then we do a collision procedure just like Stern. So we find low-weight error vectors by colliding 2 lists of elements with Hamming weight to be 2 and 3. In the first case, the cost is much smaller than Gaussian elimination. And in the second case, the cost of the collision procedure is comparable to Gaussian elimination. So this is a simulation result. We can see that this is a distribution of the number of errors in the first n positions of this reordered vector. You can think that random case, if without this information, you know that the first n position, you should have 66 is the omega ones. But you see that the number actually can be quite small. You can think in this case, if we choose T to be 3, this average number is smaller than 4. So we also simulated this success rate we need this number of oracle cores, so we target X and Y, so that's why we have this 2 factor here. Then you have these N1 blocks, and each block you need T different vectors. Here, if you choose T to be 3, then you can see that we have very okay success rate. So we need this number of traces, which is about 60% compared to the 464 for this binary PCA oracle case. So we also show result for HQC 192 and HQC 256. Now let's move on to this FD attack. This is a bit simpler, but it's much more powerful. You can see that we can output the result of all N1 Reed-Muller decoding in a single query, so there's no need to do shift anymore. So similar, we just pick key to be 0, then we have a similar setup. For this E part, we just put repeating E in each of these N1 Reed-Muller blocks, and we can get information of each block by just one query. So similarly, we optimize epsilon to maximize this entropy of this Reed-Muller decoding output. Then we construct OT for the optimized epsilon. So the key space is divided into more partitions. In this case, we actually we can decode to 27 messages, 27 Reed-Muller decoding outputs. So we get more information. It's roughly 120 bits per oracle core. This is much larger than 1.9 bits for MVPC and for 1 bit for binary PC. So similarly, unlike case, we just set up these things and queries oracle for T times. Similarly, by checking this offline templates, we can get corresponding conditional probability. We multiply them, get this reliability score, and we feed it to this ISD algorithm, then we can solve. So this is simulation results. You can see that this is super good, that for HQC 128, you just need T to be 1. It's the error, you just have 2 errors in the first positions, N is like around 17,000. So this is super good. It means that if you choose T to be 1, you have a fairly quite good success probability. So it means that you just need 2 traces. And we show results for HQC 192 and HQC 256. We need 4 traces. So we validate this attack in Cortex in the chip whisper platform, targeting a Cortex M4 CPU, and we run this PQ clean implementation and with this highest compiler flag 03. So for leakage-wise, if you consider MVPC, actually it's known that MVPC can be constructed in multiple places. For instance, you can have this leakage from encode and encode function in this re-encryption part. You can have code decode function in this decryption part. You can have this PRG generation in this re-encryption part. So we just pick this code and encode function, and we use a deep learning model, have a perfect one-trace classification. Its accuracy is 1. So it means that we just need this amount of traces. Then for FD attack, it's kind of newer. So we also observed 2 leakage sources from this code and decode functions. One from this outer Reed-Muller decoder. Actually, it's about computing the syndrome. And another from this inner Reed-Muller decoder, but this is a secondary, slightly weaker. So we use primary, or this, this primary leakage is very long and includes 30 iterations. So we just took leakage from 3 iterations, and we can have very good, near perfect success rate for recovering 45 blocks. We cannot use this leakage to recover the first block, but we can use the secondary leakage to recover the first block. It's slightly worse, but still quite usable. So if you look at this success rate, you see that for MVPC, the simulation results and the experimental validation results, they meet very well. But if you look at this FD case, this experiment part is slightly worse than simulation part. The reason is just in simulation, we all use perfect oracle, but in experimental validation, we have one block is like 86. Yeah, the oracle accuracy is 86%. It's not as good as a perfect oracle. But still the success rate is still quite fine. So let's conclude the work. We proposed the very first MVPC and the FD oracle attacks on HQC. To our knowledge, this is also the very first attack on code-based CHES. And we maximize the information gain and also greatly reduce the number of required traces. And actually, the new MVPC oracle holds significance beyond the side channel attacks. It has significance in parallel key mismatch attacks. It has also importance in fault injection attacks. And we validate the attack on Cortex M4 microcontroller, showing that this is really practical threats. Thank you very much. Happy to answer questions.
All right, are there any questions from the audience? Okay, I'll start with the first one. I will repeat the question from before. Do you know of any countermeasures that would prevent this attack?
I mean, I would say, like MVPC, it's quite. I think it's quite. Masking can be, but if you consider like. If you consider Kyber has FD oracle attack. So if you consider FD oracle attack on Kyber, then without masking, you need like 7 traces. With masking, you may need 12 traces. So it's good, but yeah.
Well, that doesn't sound very good.
but this is much more difficult for HQC, I would see, because this part is super long, super strong, and it's millions of clock cycles for unprotected. If you protect it, maybe you need tens of millions of clock cycles. And I'm just thinking now you just need 2 traces, you increase it to 4 traces.
Okay.
That's my opinion.
Any other questions? All right, then that will conclude this session and we can go to the coffee break. Thank you everyone for your questions and for attending.